Okay, today we're going to take our solving equations to another group of application problems called the distance, rate, and time. And there are basically three types of problems that we'll talk about. Down here from science, I'm hoping that you remember that distance equals rate times time. So think of rate as speed, miles per hour. Think of time as time, hours. If you take miles per hour times hours, the hours cancel, leaving miles, and that's why distance equals rate times time. So if you multiply an object's speed by its time, you will get its distance. So we're going to use this formula for all three types of problems as we apply equation solving to distance, rate, and time problems. Now we're still going to use our 5 steps of a word problem, but we're going to actually add something on these problems. We're going to start by defining a variable, but we are going to make a distance, rate, and time chart. And I am mandating that because not only does it help people to be 100% successful, it also gives me an opportunity that if you had an oops, I can find it. So distance, rate, and time table will come second. We'll use the table to write an equation. We'll solve it using all of the steps that we've been using. We'll check our solution, and boy, is it going to be important to answer the question this time. So here is an example. I want you to imagine you're sitting at an airport and you watch an airplane that takes off. You wait and you wait and you wait. And an hour later, a jet takes off, same direction, different altitude. We don't want to crash here. And eventually, because the jet is going faster, it catches up to the airplane. I call this the catch-up problem. The book calls it equal distance. But basically, we're going to have an airplane. It's going to leave the airport and it's going to be flying at 180 miles per hour. A jet that flies at 330 miles per hour is going to leave an hour later. The jet follows the same route, but at a different altitude. And here's our question. How many hours will it take the jet to catch up to the airplane? Now, right off the bat, when I read that question, that's going to be my unknown. The number of hours for the jet to catch up to the airplane. And if I make that my unknown, my answer to my solution steps will answer the question asked. So this is what I call a distance, rate, and time table. It's going to be 3 rows by 4 columns. And the first row is what I call the qualifiers. What are we working with? In this case, it's an airplane and a jet. The rate, also known as speed, will be the first column. Time will be the second. And I put distance out at the end. So I kind of spin this around because we're going to fill in these cells. And how we fill in the distance is to multiply the rate times time. So whatever we put here and here, we multiply and we'll write it in that cell of the table. So then we're going to write an equation once we have the table filled in. So let's go back up and see what can we fill in from the information. So where does the 180 miles per hour go in the table? It is a speed, so it has to go in here. And since it's the airplane, we would put it in that cell. Are you with me? Now notice that I put the units for the speed. Sometimes that's helpful in case you end up with mismatch units. The jet speed will go in the cell that says, jet and rate. So now what about the time? Well, I said T is the hours for the jet to catch up. So I come down to the jet row, over to the time, and I'm going to put T in there. Now I'm going to warn you, the next step is often the mistake step. So I want you to picture what's happening. The airplane takes off. It's flying, it's flying, it's flying, it's flying. Hour later, the jet takes off. Who was in the air flying longer? Who has more time in the air? Did you say airplane? So that extra hour has to get added to the airplane's time for the time in the air. Some people get confused and think of clock time, but we're talking about how much flight time was happening here, and the airplane was up there an hour longer before the jet caught up. That's the toughest part, guys, because now to get the distance, we're going to just take our rate times time, and make sure you put parentheses. You're multiplying the entire time. So this is going to end up being a distributive property. And on the bottom, 300 times t. That's how we fill out a distance, rate, and time table. Now we need to ask ourselves, look at the distance. Did these two planes, plane and the jet, fly the same distance? So they left at the same airport and the jet caught up. Did they fly the same distance? And the answer is yes. So what do we do with their distances? We set them equal, and voila, there is our equation. Now, if I gave you that equation, I know you know how to solve that. So let's do that next. Step 3 of our problem solving 5 steps. So I'm going to take that equation and I'm going to do the distributive property. And now I notice there's a variable on both sides. I'm going to guess. I'm going to subtract the 180t to keep it positive. I did. And then I look here, the 150, I'm going to divide both sides by 150. I mean, I can simplify the fractions, but I'm going to pick up my calculator, and 6 divided by 5, or 180 divided by 150. I'm going to make it 1.2. So we'll come right back to that in a second, but let's do our check, which is our 4th step. We're going to put that 1.2 in for t on the left, t for the right, and make sure that we did our steps correctly. And when I do that, sure enough, not using the distributive property, using PEMDAS, adding those and then multiplying, I get the same number on both sides. I'm going to come back and talk about this in a second, but let's answer our question. So let's go back and figure out what the question was. How many hours will it take the jet to catch up with the airplane? So if I go to the jet, to its time, I just need to give the t. And since I was strategic in putting the unknown where the question asked, then I already have the answer, in this case, to the question. So it would catch up in 1.2 hours. What if I had given you the time, though? What if I said that the airplane had left at, 1 o'clock? And you had to give me the time that the jet caught up? That could have been a different way to ask this question. Everything we've done, we would have done the same way, except we kind of need to know what this is in minutes to be able to add it onto the clock time. So just remember, all you have to do is take that 0.2 times 60, and that will tell you how many minutes. So if you needed to kind of use the clock time, you would have to convert that 0.2 to 12 minutes, 0.2 times 60. This question didn't require it, but I wanted to make sure I told you that. Now remember I said I was going to come back and talk about this. So there were several questions I could have asked here. I could have asked the one that was asked, how many hours for the jet? I could have asked how many hours for the airplane. Now, if you had set it up the same way, you can still answer that question. Just 1.2 plus 1, it would have been 2.2 hours. But I could have also asked how much distance did they fly? And it wouldn't matter which one I use here because the distances should be equal. But if I had asked that question, how much distance, I would have done this problem the exact same way. But my answer of my question is actually sitting right here because I put the 1.2 in and I put the 1.2. Notice it's 396. That's how many miles the plane and the jet traveled from the airport to when they were at the same distance from the airport, 396 miles. So there's different questions you can ask. So you really need to make sure that you don't just go moving on. Go back and read the question and make sure you're answering the correct question. Okay, so the second type of problem is what I call the round trip. I think the book calls it equal distance. I also call it the up and back because of this problem. So imagine you're going to go hike Lantern Hill. And as you're hiking, you go up the hill at 4 kilometers per hour and you look out at beautiful scenery, and then you come down and you're going 6 kilometers per hour. Why would you be going faster? Because you're going downhill, people, right? Uphill's tougher. So it's not a surprise that you would be going downhill faster. The entire trip up and back took 3 hours. How long was the trip up the hill? There's our variable. How long? Time. And we're talking about hours, right? So we want to know how many hours it took to go up the hill. That's going to be our variable. Now here is my table, 3 rows by 4 columns. And here is just those qualifiers. This time it's not a jet and an airplane, it's up and it's down. So do I have information to fill in? So I'm going to ask you, I'm pointing to this block right here, this cell. What would I put in the up rate? Did you say 4 kilometers per hour? What would I put in for the down rate? Did you say 6 kilometers per hour? That was pretty easy. What would I put in for the up time? What would I put in this cell? That's our variable. That's what we defined right here. So now the question is, what do I put in the downtime? The whole trip took 3 hours, and the up portion took or used up T of those 3 hours. So what is left for the down portion of the time? Did you guess it? You're going to take the 3 hours of the whole trip and take away the part you've already used, and that would leave the time for the down trip. Now, how do we fill these cells in? Easy peasy. We're going to take rate times time to get distance. We're going to use that formula we know is true. And we're going to do the same thing here, but be careful to catch the 3 minus t in the parentheses. Now, my question is, if you go up the trail and come down the same trail, what's true of your distance up and your distance down? Did you think equal? Yeah, like the trail didn't magically change while you're at the top. So the distance up is going to equal the distance down. And now we're off and running with our algebra steps. So step 3, we're going to solve it. What I'd like you to do is to solve it, check it, and can you go back and answer the question asked? When you're set, unpause the video and we'll check out how you did. All right, distributive property. Now, I did this on purpose. I know some of you just use the minus. Some of you like to change it to plus and negative. It is A-okay. I just wanted to mention that, so that's why I did it on this one. Did you distribute to that second piece? Make sure you don't just have a minus t here. And now I've got a variable on both sides. I'm going to guess that I added 6t. Did I? I did, to keep that coefficient positive. I'm going to divide by 10, and don't be surprised, real-world problems rarely come out to the answer of 2. So in this one, you're going to notice you came out with 1.8. I'm going to put that back in on the left-hand side and the right-hand side for my t's. I'm not going to do distributive property. I'm going to subtract and then multiply, and sure enough, I've got 7.2. All right, we need to answer the question. Our t is 1.8. Let's go back. We need to know how long was the trip up the hill, time. We just use our t. So our t of 1.8 hours is how long it took to go up the hill. If we needed to have that with minutes, take the 0.8 times 60, and it would be 1 hour and 48 minutes. Now, I could have asked you other questions, like what was the time going down the hill? Then you would take 3 minus the 1.8. And the distance, you would put the 1.8 in here, but remember that that happens in the check. So you put the 1.8 in here, and you put the 1.8. The distance up was 7.2 kilometers, I think it was, and the distance down was also, of course, 7.2. Was I right with the kilometers? I was. So that is an up and back or round trip problem. And notice in both the first 2 examples, the catch up with the jet and the airplane and the up and down Lantern Hill, we set the distances equal. Let's go to our third type of a problem, which is the weirdo. He's completely different than the other 2. We're still going to use the table, but something different happens with the distances. I call this the opposite direction problem. I think the book does as well. This one is going to have the objects moving away from each other, but please know if they were coming towards each other, it would still be an opposite directions problem. They're not going the same direction. So two jets are going to leave the airport at the same time. So you're sitting, let's say, at the Hartford Airport, Bradley, and you're watching, waiting for your flight, and you see two planes, two different runways, and they leave basically at the same time going in opposite directions. One of the planes is going to fly west, and that plane is going faster by 50 miles per hour than the other plane, which of course would be going east. Now imagine if you could, after 2 hours, you kind of take a picture and see where they're apart. And at that point in time, they're 2,500 miles apart. The question is, find the speed of each jet. Now I need two answers here. You got to pick one, and there's no wrong. You could pick, I'm going to let S be the speed of the east. You could have let S be the speed of the west. But at the end, you're going to have to come back and remember you need both of them. So now we're going to fill out our table. Now these qualifiers, jet 1, I'm going to call the east going jet, and jet 2 is going to be the west going jet. So now can you put the appropriate speed into the east speed, please? And the appropriate speed into the west speed. Okay, let's see how we did. S would be the east going because that's what I defined it to be. Now, what about the west? Let's see, the west is going 50 miles per hour faster than the east, so I would have to add the 50. Now, if you had defined the variable the other way around and put the S in here, then you would have had to put S minus 50 in the east. Are you with me? So you still can get there. Now the question is, what's going on with the time? After 2 hours, they're 2,500 miles. You stop them. So guess what? The east going flew 2 hours. Guess what? So did the west. So now how do we find the distance out here? This is the easy part. This is where we're going to use our formula. We're going to take speed times time. Rate times time is going to give us distance. Oops, sorry about that. That's being a little persnippety. And then speed times time. And remember this one in a minute, we're going to have to use a distributive property. So make sure your parentheses are in here. Did they fly the same distance? Did they fly the same distance? If one of them is going faster, if one is going faster than the other and they flew for the same amount of time, are they going to cover the same distance? And the answer is the big no. The one that is flying faster is going to cover more distance. So we do not set these equal to each other. So there's another number up here. Do you see it? So the east jet's distance and the west jet's distance have to combine to get the total distance that they have gone apart. So distance 1 plus distance 2 will equal the total distance. And now we're running off to the races with our algebra steps. So distributive property and like terms. So I'm going to click to a new slide. I'm going to ask you to solve this equation, check it, and please answer the question. We'll come back, make sure you understand, and that is sort of the end of our presentation for today. Okay, did you do the distributive property? Did you remember to distribute to the second piece? Okay, like terms. Subtract 100 from both sides. Oh, this one is going to come out nicely. Divide by 4, and we get 600. Now, we're not worried about the question yet. We're going to check it to make sure we don't have a mistake. No sense answering the question if we goofed it up, so let's check it first. So we're going to put a 600 into both S spots. We're going to add, no distributive property, we're going to add and then multiply, and then sure enough, we have a good result. So let's answer the question. Remember that S equals 600. Find the speed of each jet. So I basically need these two. So east would be the 600 and west would be the 600 plus 50. So the answer to my question would be that the jet 1, which was the east, was 600 miles per hour, and jet 2, was 650 miles per hour. Now, I could have asked a different question. I could have said, what were the distances? So here, if you took the 2 times the 600, jet 1 went 1,200 miles. And if you take the 650 times 2, jet 2 went 1,300 miles, and you actually can see it inside your check. It's not the 2,500 this time because that was the total distance, but you can see the two pieces. There's east and there's west. So there are a lot of different questions I can ask. So you just have to make sure that you go back and make sure you're answering the right question. So today we applied our equation solving techniques to another group of problems called the distance, rate, and time. And we found there's really 3 categories of problems. One is the catch-up. Both objects are moving in the same direction, but one leaves earlier and the second one catches up. Same direction is the way the book calls it. When that happens, their distances are equal. They left from the same spot, and when they caught up, they're in the same spot. Their distances are equal. The second type of problem we did, which is the round trip, the up and back, Lantern Hill. Again, you're going to go up and you're going to come down. Those distances, again, are equal. The third type of problem is the opposite direction. This is the different one. This is where one object is moving either away or towards, depending on which direction they're going opposite, faster. So that object that's going faster will cover more distance. So you don't set the distances equal. This time they're going to combine, they're going to add to a total number. Your BFF will be that distance, rate, and time chart. Please make sure you're doing all the problems with that. It will be required on assessment. So guys, are you ready to practice our distance, rate, and time problems? Have a great day.